All right, we're in business. Okay, thanks for sticking around, guys. I know it's the end of the day, and I have a train to catch anyway, so I'm gonna make this real quick. But I'm here today to talk about GPUs. My name is Kelly Bryant. I'm a developer advocate for MapD very recently. But before that, I spent some time calling myself a data science product engineer. And like Jared said, I also do a lot of things for R-Ladies, specifically R-Ladies DC, and some cloud stuff for R-Ladies Global, which is pretty cool. I publish a monthly series called Our Profile on the R OpenSci blog, which I like a lot, so check that out if you haven't seen it. And I just want to hop right into it. So I'm here today to convince you to be interested in GPUs if you aren't already, or you've heard about GPUs and GPU computing and you don't know what it is yet. So let's start. I want to talk to you about what GPUs are. And when we introduce GPUs to people, oftentimes you'll do it or you'll see it done in conjunction with talking about what CPUs are. So GPU is, as you may have guessed, an acronym, and it stands for Graphics Processing Unit. GPU processors were designed for the purpose of rendering images, animations, videos to your computer screen. But in the last decade, we've been seeing them applied to a lot more applications. It's common to see them alongside CPUs, as I said. And so I've drawn up the classic CPU, GPU core comparison. So a core is just a unit on this unit that receives instructions and does the processing of calculations and performance things based on those instructions. So CPUs are often called the brain of the computer. And they have multiple cores, maybe like a couple. But those cores are really fancy, and they're awesome, and they do awesome stuff, and they're optimized for doing serial tasks. GPUs, on the other hand, may have hundreds or thousands of these cores. But don't get too excited, because they don't do all of the awesome stuff that CPU cores do. They do very basic tasks, but there's a lot of them, and they're optimized for doing parallel tasks. Here to explain the difference between serial and parallel task execution are the Mythbusters. If you haven't seen this video, it's really great. I just created 2 GIFs of it. On the one side, you see CPUs, where they have this robot that aims and fires paintballs, aims and fires to create, eventually, this rendering of a smiley face on a big canvas. And on the other side, they've created this monstrosity of a machine that has thousands of pipes with a single paintball in each pipe, and they hit a button, and all at once, all those paintballs shoot at the canvas and create a rendering of the Mona Lisa. So I don't know if that's a perfect explanation of the difference between GPU and CPU, but it is very fun. And if you watch the video online, you can hear Adam Savage just maniacally laughing after he hits the button, which is really great. But let's talk about why people are so excited about GPUs. You know, like when I first heard about GPUs, it was from my dad, actually, and I think I was in college. He's an aerospace engineer, and he does star camera stuff and some viz stuff that I don't understand. And he asked me, hey, do you know CUDA? And I was like, no, Dad, why would I know CUDA? What is that? But hearing about it again in graduate school, and then again over and over, now recently JJ gave a really awesome keynote at this past RStudio Conf, and in it he talked about how GPU computing just revolutionized the field of computer vision through deep learning. If you haven't seen that, that's also available online. I highly recommend it. It's long, but it's worth it. So people are doing really cool stuff with GPUs. And here's some other things that they've done. So I want to talk about what problems GPUs are good for now. What applications have people found for them? First off, they started being a graphics card. Then people discovered you could do high-performance computing with them. From there, we discovered applications in machine learning, revolutionized deep learning. From there, even further, general purpose computing for big data analytics, and finally, database operations. So today, I want to talk about those last 2 kind of pieces further on. But first, just kind of to sell you on this, like, I know that a lot of people get up here, people from the data science industry, and they say, you know, we're all dealing with big data. And like, I want to be real. I know a lot of people in this room probably aren't day-to-day dealing with big data. But this was one of the quotes that came out of our profile project, my interview project with our OpenSci. The interview was actually conducted by Sean Cross, but it was with Dr. Julia Stewart-Lowndes. And I love this quote from her where she says, "I learned to code in a total panic because my data was too big to be opened in Excel. So because I was trying to figure out science and coding at the same time, I conflated research with data science. I was confusing my thesis questions that no one had ever asked before with data questions that many people had asked before and solved." So if anything comes from you attending my talk today, I hope that, like, even if you aren't ready for big data analytics, like, maybe someday you will be, and you'll remember the stuff that I've talked about today, and you won't be lost in this total panic where you don't know what to do and you think these problems have never been solved before. So with that, how much does it cost? I love Wired magazine. I read it all the time. This title from an article in 2013 really got me, though. It was, "Now you can build Google's $1 million artificial brain on the cheap." How cheap, you say? Only $20,000. And by you, I mean Andrew Ng. Yeah, so when I was reading this in grad school, it kind of pre-biased me to think, like, oh, GPU is really cool. There's a lot of computer vision applications, but it's probably not for me yet. I'm a student. I don't have this kind of cash. And so I kind of went along with that assumption for a good number of years. But it's 2018 now. So what has happened since then? There are ways to get access to GPUs now. And I've sort of listed these in order of harder to figure out down to easier to figure out. And you can argue with me afterward whether I've got these in the right order. But these are kind of my personal experience. GPUs are a component on your computer. Perhaps there's one in your computer that you can use. Now, I've read that these things are more difficult to figure out than just that, and some of the graphics cards on your computer might not be optimized to work in that way, and so you have to do a lot of Googling. I haven't bothered to do this. Second, you can go out and buy these things. NVIDIA sells them, and you can buy one and own it and keep it in your domicile and take care of it like a pet. I don't know. I don't touch hardware. You could. Now here we get into the space that I am comfortable with. So you can go and rent this hardware from a cloud service provider, and you can do it pretty cheaply. Here's Amazon Web Services. You can get one for 90 cents an hour. They go up more expensive than that, obviously, pretty quickly, but 90 cents an hour. Very reasonable. Here's some from Google Cloud. All the major cloud providers have them. Azure has them. I don't have a slide for Azure. But they're all out there, and they're ready to be rented, and you can go and learn the skills to rent them very easily. But I do want to caveat this with a couple of other thoughts. Like, when you, or I'm assuming most R users are going to be doing GPU compute in kind of a hybrid way, where most of your R code is, or a bunch of it will happen on CPU. So doing CPU R, and then maybe you have a set of functions or processes that GPU compute might be useful for. So the hybrid approach would be lots of R on CPU, and then you flip over, do some GPU stuff, but you're not using it all the time for everything. So you have to sort of think about, like, what is your usage going to be? What are your needs? What are your team's needs? And sometimes those can be very hard to predict. So are you leaving it on all the time? Are you turning them on, turning them off? You have to learn these cloud computing skills, which I'm a big proponent of. I wouldn't be an NYR talk for me if if I didn't get up here and like evangelize about cloud computing. So you have to get over your fear of giving them your credit card. It's okay. And then you're probably going to waste a lot of time learning about this stuff, and you're probably going to make mistakes, and that's okay too. But learning about the cloud and how to use R in the cloud has really changed my perspective on data science and opened up a lot of avenues for me personally. So I'm a big proponent of it. The last one is kind of an interesting thing, and it's fairly new, but there are now services that you can subscribe to where you get hardware, GPU, and software as a subscription service. So here's the service offered by MapD, my employer, where you can subscribe to a monthly tier system where you choose how much data you want to ingest, and then they give you a rate based on that. So I do want to talk now about GPU-powered SQL engines. And this is kind of the core of what I do as a developer advocate for MapD. I work with their MapD core open source database. And I try to get people excited about using it and trying it out. So MapD has created this SQL database that is GPU powered. And the cool thing about that is that not only can they do things with big data, process SQL queries very fast, but you also have access to not only the compute pipeline inside the GPU, but also the visual pipeline. So you can do a query in SQL, and then very quickly, not even having to copy, transition to the graphics pipeline and create a visual rendering, which is really awesome because the application for that is then doing exploratory analysis on big data. So I want to do a demonstration of our open source database and a visualization platform that is not open source, but is a great addition to sit on top of our open source database and provide you with some of the the visual power, so showcasing the visual power of the MapD open source database. So this is 11 billion rows of data that I'm visualizing. And the reason we could do this is the MapD database is doing the rendering on server side. And it's kind of a hybrid visualization approach where all of the fancy visualization rendering gets taken care of, compressed down on server side to about 100 kilobyte static PNG. And then it gets sent client side so that we can interact with it very quickly, and it feels like real-time human interaction with data. So we could do things like filter very fast, take off the filters, zoom to New York City. And obviously, you're probably thinking, like, Kelly, you can't show 11 billion points on a screen. Like, that doesn't work. So yes, these are layered, but you can zoom around, and it will show you things. There's even some really fancy stuff they do where you can show some metadata about different points and brush over certain periods of time. So yeah, I think this is a really powerful platform. You know, what it's lacking is kind of community support from data scientists, from people like the R community to come in and try things out and to give feedback on what these platforms are missing. Like, there are a lot, it is in very early stages, so that kind of feedback would be really useful, and I think it is really important for the R community to become involved in projects like GPU computing, especially open source projects, so that we can have a say in like what happens and how data science is affected by GPU computing and how we can get it very quickly into our own analyses and use it. So with that, I want to say, please reach out if you have any use cases that you think would be cool fits for this kind of solution. We have our open source projects, which are available on GitHub, and we have a vibrant community over at our forum. So we need our folks. It would be great to hear some of your voices in our community. And with that, thank you very much.